Okay, part two. So part two of 4.4, we are going to go the way that we went in 4.3. So instead of going from zeros back to polynomial functions, we're going to go from polynomial functions to zeros. And before we could do that, there's one more thing that I have to teach you. So if you remember way back in 4.3, let me just scroll back here. No, a little bit further back. I gave you steps to how to factor a polynomial. So step number one was to use the factor theorem to find a factor of the polynomial. You can find factors by using the remainder theorem. That was something like f at 1, does it equal 0? Question mark, right? You could use long division. If you divided in, is your remainder 0? Or you could use synthetic division, and you could say, is your remainder 0, right? That's the whole factor theorem. So it's something that would give you a remainder of 0. I recommend using the remainder theorem or synthetic division to do this. I would never use long division. And I told you that when you're trying to find numbers that are potential factors, so if you're trying to find the zeros is what we're doing here, you're going to choose numbers that are factors of the constant. So something like multiples or factors of -6, so plus or minus 1, 2, 3, and 6. And then we use synthetic division, then we factor. Well, all of those steps are going to be true today, but I have to add one thing to it. So I can get back there. That one thing is that I didn't tell you the whole story there. When I told you that potential zeros are always like the factors of your constant, so plus or minus 1, 2, 3, and 6, that wasn't the whole story. What it is there's actually potential rational zeros as well. So this gave you all of your potential integer zeros, and you're always hoping, like fingers crossed, one of these works, but sometimes one of them doesn't. And so you have to go a bit farther to see what are the other potential factors. And so what you do is the rule is the rational zeros theorem states that P over Q are possible factors of your polynomial, where P is a factor of your constant, A naught, and Q is a factor of AN, which is your leading term. Well, it's the coefficient on your leading term. So to find all the possible rational zeros for this function, you take all the factors of your constant, 6, and you list them. And then you divide that by all the factors of your leading coefficient. So all the factors of 2, which would be plus or minus 1 and 2. And then this will give us the whole picture. So you divide. So the nice thing is that all of these are, of course, correct because you're dividing by 1, right? First off. So potential factors are plus or minus 1, 2, 3, and 6. And then you also divide by 2. So a half. 2 divided by 2 is 1. We already have that one. 3 divided by 2. And then 6 divided by 2, which is 3, and we already have. So there's 4 new zeros that we didn't try before. Now, 90% of the time, one of these nice integers will work, but there is that 10% of the time where you have to go to the rational zeros. None of these integers work, and so you have to search further, and one of these might work. And I say 4 new ones because it's plus or minus, so plus or minus a half, plus or minus 3 halves. All right, so let's do one. I have a polynomial function here, 2x cubed minus x squared minus 6x plus 3. I want to find all the rational zeros and then the other zeros. In other words, I want to solve this equation, and then I'm going to factor this into linear factors. Okay, so I'm going to do the process of 4.3. The first thing I'm going to do is find a factor. So I'm going to use the remainder theorem to plug in values of x and try to get a remainder of 0. What values should I plug in? That's the question. Well, it could be anything that is a factor of 3, which is 1 and 3. And it could also be divided by anything that's a factor of 2, which is 1 or 2. So altogether, my possible rational zeros are plus or minus 1, 3, and then 1 half and 3 halves. Okay, so there's only 8. There's 8 potential rational zeros. That doesn't mean there couldn't be some that are imaginary or irrational, but these are all my potential rational zeros. Okay. So what you then have to do is you start plugging them into the equation. You try 1. You're like, okay, if I plug in 1, I get 2 times 1 minus 1 squared minus 6 times 1 plus 3. Does that equal 0? No. And in fact, I can tell you that 1 doesn't work. Negative 1 doesn't work. 3 doesn't work. Negative 3 doesn't work. So if you plug in any of these, they are not going to work. So negative 1 doesn't work. 3 doesn't work. -3 doesn't work. Okay, I picked this question because it's one where none of the integers give you a remainder of 0. So let's start trying the rational zeros. Let's try a half. If I plug a half into this equation, I get 2 times a half cubed minus a half squared minus 6 times a half plus 3. Now, I don't want this to be a laborious process. I don't want you doing that by hand. You have a calculator, use it. It's okay to use a tool that you're given because I don't want this to become a long and lengthy process. So I would plug this in as 2 times 0.5 cubed minus 0.5 squared minus 6 times 0.5 plus 3 gives me 0. So there's my 0. So the first one that works is a half. So now that I have a 0, I have my first factor. Because if you think about it, this polynomial, sorry, they used f, didn't they here, not p anymore. So this polynomial is f of x equals 2x cubed minus x squared minus 6x plus 3. And we know that we're going to then find a factor, take it down to a quadratic. And then we're going to take that quadratic down to its linear factors. This is going to be our goal for b, right? This is b. What we just found is the first one. So we found that the first factor is going to be x minus a half. Now we're going to do something with that in a bit. So just be mindful, I might have to change these brackets. But this is our end goal on most of them. This one just has a small tweak. Okay, so now we have to figure out what's my quotient. What's going to be left when I divide 2x cubed minus x squared minus 6x plus 3 by x minus a half. So I'm going to put a half into the little box. I'm going to pull off my coefficients. 2, -1, -6, 3. And then I'm going to pull down. I'm going to multiply. I'm going to add. I'm going to multiply. I'm going to add. I'm going to multiply, and I'm going to be breathing a sigh of relief because I got 0, right? It remains, like, this is a way of checking your remainder theorem, is that when you do the synthetic division, you should end up with a remainder of 0. Now, what are these 2, 0, -6? These are the coefficients on my quotient. So I took an x cubed polynomial and I divided by x. So this is going to start with x squared, x, and then my constant. So this next line is going to be 2x squared minus 6. Okay, now before we go on with this, one thing I want you to notice, is that we're trying to factor this, right? And if you look at this right now, do you notice anything about this factor? Is it fully factored? Could I find a greatest common factor? In fact, yeah, I could greatest common factor out of 2. So I'm going to take this 2, and this only happens very rarely, so just be careful when this does. If I can take out a factor of 2, I'm going to take it out. I'm going to write it out front. I get 2 times x minus a half times x squared minus 3, right? 2x squared divided by 2, -6 divided by 2. Now, because what I want you to notice is that this polynomial doesn't have any fractional coefficients. And so to make that happen, you actually have to do this. So I take the 2 out of there, and now I can multiply this 2 back in. And I end up with 2x minus 1 times x squared minus 3. Okay, so now I have factored my cubic function down to a linear and a quadratic factor. Now I have to go further. So in 4.3, you would have looked at this and been like, oh, it's factorable. But in 4.4, you might look at it and be like, I can't factor that. Now, some people might be able to. By no means you can't. Like, it's not, it should be a difference of squares, and it's not. But you can still use the process of factoring a difference of squares to do this one. But what they want you to do this is find the zeros. And so to find the zeros, what you do is you set that equal to 0. So we've got 2x minus 1 and x squared minus 3. And to solve this, you set each factor equal to 0. So what makes 2x minus 1 equal to 0? When 2x equals 1 and when x equals a half. So there's my half 0. And then we do this guy too. What makes x squared minus 3 equal to 0? When x squared equals 3, and then take the square root. So when x equals plus or minus root 3. So I got 3 zeros, which matches the fact that this was a cubic function. So when you have a cubic function, you should get 3 zeros. Some of them might be imaginary, some might be irrational, but there's always going to be 3. Okay, So now what I can do is I can take what we just learned to say, okay, well, 2x minus 1 is one of my factors. And then to write this as a product of linear factors, I could put my x, minus, and then put my zeros in. So x minus root 3 and x minus root 3. So then I've taken my polynomial function and I've factored it down to a product of linear factors. But the thing that was new in 4.4 is that when you got to here, you couldn't factor that in the traditional sense. It wasn't a difference of squares. It wasn't a trinomial. It wasn't anything that you could do by grouping, right? And so we used a different skill. We solved for the zeros and then we put them back in to make linear factors. Now, if you looked at this and went, hey, that's a difference of squares, that one's just not a perfect square, you could factor it by going bracket, square root of the first term, x, and square root of 3 is root 3, and then put plus minus. That's totally fine. But this was the process that you were supposed, well, I'm doing supposed in air quotes. It doesn't really matter, okay? But the question asked you, find your zeros, right? The rational ones first, which we did. We found a rational 0 1/2, and then we found the other zeros, which were irrational, and then we wrote it as a product of linear factors. Okay, last one. So here's another one. This one is going to be a little bit easier, I hope, in some ways, because A, there's only a few rational zeros that are potential, and this isn't, like, it's not going to be a fractional zero, so it's going to make it a bit easier. So the first thing we're going to do is the remainder theorem. So the remainder theorem, you got to find potential zeros of this polynomial, and you do that by taking factors of your constants, so plus or minus 1 and 17. Those are the only two numbers that multiply to give you 17. And dividing that by the leading coefficient, which is plus or minus 1, right? That's why this one only has 4 potential zeros, plus or minus 1 or 17. Now let's do it. So let's try plugging in 1. When I plug in 1, I get 1 cubed minus 5 times 1 squared. Sorry, I don't do that because squaring a 1 isn't going to do anything, but I should. Okay, so I'm putting in a 1 plus 11 times 1 plus 17. Now I can tell you right away that's not going to work because I've got plus 28 and nothing to balance it. So that's not going to be 0. So let's try negative 1. So if I plug negative 1 into here, I get negative 1 cubed is negative 1. I get negative 5 times positive 1, because negative 1 squared is negative 5. And then I get 11 times negative 1 is negative 11. And then I get 17. And that one works. Yay! So I'm on my way to factoring this, right? So right now I already know the first factor. The first factor is x plus 1. I have to figure out the quotient. So to do that, I do long division. Negative 1. Pull off your coefficients, you get 1, negative 5, 11, and 17. Synthetic division. Pull down, multiply, add. Multiply, add. Multiply, breath of fresh air or relief or exhale, I get a remainder of 0. Which means that when I did an x cubed divided by an x, I'm going to start with x squared, x, and then a constant. That's what's left. So when I divided that polynomial by x plus 1, I got x squared minus 6x plus 17. Now I'm down to a quadratic. So as soon as you're down to quadratic, what you want to think of is, can I factor this? So can I factor this as a trinomial using the AC method? Are there two numbers that multiply to give me 17 and add to give me negative 6? No. No. So instead, to factor that, I have to find its zeros. So to find the zeros, I'm going to solve x squared minus 6x plus 17 equals 0. So x squared minus 6x plus 17 equals 0. I'm going to find the zeros. You have two choices. You can complete the square, or you can use the quadratic formula because it doesn't factor. You can't use the square root method. So you have to use one of those. So I'm going to do it both. So I want you to pause the video. When you unpause, I will talk through solving by completing the square and the quadratic formula. But try it on your own first. So if I was going to do completing the square, I would go x squared minus 6x. I'm just going to take that 17 to the other side by subtracting 17. I take half the middle term squared and I add it to both sides. Or you can add and subtract it on one side, it doesn't matter. Then I'm going to factor that to x minus 3 all squared. And then I've got negative 17 plus 9 is negative 8. Then to solve for x, I'm going to take the square root. So I get x minus 3 equals plus or minus the square root of negative 8, which I'm going to simplify. So x minus 3 equals plus or minus 2 root 2i, right? Highest perfect square that goes into 8 is root 4, root 4, root 2, root negative 1. And then isolate x. X equals 3 plus or minus 2 root 2. Hi. Okay. Or you could have used quadratic formula. So if you use the quadratic formula, always write it down first. Negative b plus or minus the square root of b squared minus 4ac all over 2a, which gives me negative, I have to be able to see it. So the opposite sign of negative 6, so positive 6 plus or minus the square root of negative 6 squared minus 4 times a is 1 times c is 17 all over 2 times a, so 2 times 1. All right, what does my next line look like? Well, I've got 6 plus or minus the square root of 36 minus 4 times 17, which gives me negative 32 over 2. All right, now we're going to simplify. So the highest perfect square that goes into 32 is 16. So this is going to be 6 plus or minus 4 root 2i all over 2. Then I'm going to greatest common factor 2 out of everything to be left with 3 plus or minus 2 root 2i. So I got the same answer. So it doesn't matter whether I did it this way or whether I did it this way. I get that as my zeros. Now to finish this off, right, I want to finish this off as a product of linear factors. Now I don't have enough room if I do it there, so I'm going to do it down here. So f of x is going to equal my first factor, which was x plus 1. Let me just double check that. Yes. And then my other ones go like this. X minus, x minus. Okay, one of the zeros is 3 plus 2 root 2i, and the other one is 3 minus 2 root 2i. Then I'm going to simplify, so I get x plus 1 times x minus 3 minus 2 root 2i times x minus 3 plus 2 root 2i. And that's my final answer. So this question didn't ask me for the zeros. If it did, I could have stopped at negative 1 and 3 plus or minus 2 root 2i. This asked me for just the linear factors. So if I wanted to check it, if I multiply it back out, I'll get this. So literally, I just took that and put it in factored form. So if I multiply this back out, I should take it back to the polynomial function. And that's it. So this one had one real zero, so there's only one place you'd cross the x-axis, and then the other two are imaginary. So they won't affect your x-axis, but they will make it a cubic function. So without those imaginary zeros, this wouldn't be cubic, right? It would just be x plus 1. It would be linear. So we need them. They hold places so that when I multiply this back out, I end up with a cubic function. All right, I would definitely practice these 5. I picked out very few questions because they do take a long time, but I would do all 5 of them.